My name is Jerome Sheehan, and I will be going over Lab 3 beam vibration. For the outline, we have the laboratory objectives, experimental setup, experimental results, and for these results, we're reviewing the static measurements, dynamic measurements, vibration control, and then finally the summary, conclusion, and references. For the objectives, we are going to take measurements for multiple free vibration experiments through 4 cases. We're going to measure tip deflection using a strain gauge, compare tip deflection to theoretical deflection, and determine the natural frequencies via the spectrum analysis of time-dependent tip displacement. For the experimental setup, we used the MSP432, which was attached to a Wheatstone bridge, which supplied voltage and also read voltage across R1, R3, R2, and R4. We used 120 ohm resistors for R1, R2, R3, and then R4 was, of course, the strain gauge. As you can see in the bottom right, we have the Wheatstone bridge setup, and then in the bottom left, we have the experimental setup, which in red there, you have the MSP432, and then the clips and resistors making up the Wheatstone bridge. For the second part of the experimental setup, we have the beam. The goal here was to simulate a cantilever beam. This was done by creating a fixed end on the table with a clamp, a wooden block, and a metal block. And this is not a perfect fixed end, but it is close enough. Finally, the ruler tip was then deflected as a opened source. For the final part of the experimental setup, we have the displacement. The displacement was found by placing a small table underneath the ruler, then measuring from that table at an undeflected position of 6 inches and 2/10 of an inch. And then once deflected fully, it was 5 and 5/10 of an inch. And this is a seventh tenths of an inch deflection. The strain gauge sensitivity was need to be found to convert the voltage into displacement. This was found by measuring the deflection of 5 points, which the data can be seen in the sensitivity table, and the voltage, and then creating a slope or a line of best fit to find the sensitivity. Um, the assumption here is that the relationship is linear, and as you can see from the sensitivity graph, the raw data is not perfect, but it does end up being a linear fit. Next, we have the beam stiffness equivalent. This was needed to be found to equivalent the cantilever beam to a spring mass dampener system. Similarly uh, to the sensitivity, a linear relationship was found between force and measured deflection, and then this allowed us to find a constant K value or stiffness value. The assumption here is that the mass is all located at the tip of the beam. Here we have the dynamic measurements, the initial displacement excitation for case 1. The initial displacement can be seen in blue in the first 5 seconds of the beam vibration graph. That is when the um, beam is actually displaced 7/10 of an inch. And then once the graph turns red and you get to about 0.5 of a second, um, the beam is let go and vibration is seen. In order to find the dampening ratio, natural dampening, and the natural dampening ratio, we had to take this beam vibration data, isolate the peaks, and then curve fit a slope to the middle peaks. This slope data was then used to find the 3 parameters listed. They can be the dampening ratio equation can be seen right below the dampening ratio, and then this was done by taking the curve fit of the slope and then applying it to the dampening ratio equation. The damp natural frequency was done in a similar manner where you have one, the inverse of the mean of the difference in the chosen peaks, and the natural frequency was using the curve fit again to find the natural frequency times zeta and then divide that by zeta. Each of these cases were determined to be underdamped since the dampening ratio was less than 1. For case 1 here, the initial displacement excitation, the theoretical displacement was found and plotted over the experimental data. As you can see, both of them are very close at the very beginning and at the very end. Um, this data suggests that the dampening ratio may be off slightly, or the fixed end uh, may play a role in the experimental data not fitting perfectly to the theoretical. For the initial displacement excitation for the spectrum, you can see that there are two main peaks, one at 13.8 hertz, one at 88.7 hertz, and this shows that there are two fundamental frequencies in this graph, and both of them happen to be very close to the predicted frequencies as seen below. For the impulse excitation, a coin was dropped 6 inches above the beam, and then um, the beam was displaced. As you can see, at the beginning, there's zero displacement for about the first second and a half, and then once the beam is struck by the coin, that vibration is rapidly increasing, and then you get that oscillation. For the impulse of the For the spectrum of the impulse excitation, you can see three distinct fundamental natural frequencies. They occur at 13.4, 88.9, and 249 hertz. And again, these were very close to the predicted fundamental natural frequencies found in the pre-lab. For the final case here, we have viscoelastic dampening. Two different tapes were used, duct tape and carpet tape. Both um, the carpet tape being slightly stronger than the duct tape. Both cases, 4 inches of tape were applied, and then uh, the same 7/10 of an inch of deflection was applied as well. The results from these experiments are compared here. With no tape, you have a small dampening ratio, but as you get duct tape, that increases slightly and then increases even more with carpet tape. And these can be seen by the amplitudes of the graphs being similar at the beginning, but then for the carpet tape, the vibrations decrease very rapidly compared to others. For the summary for all cases, you have case one and two, which you would expect the dampening ratio to be similar since nothing was changed with the actual beam. It was just the two different ways of measuring deflection. One of the reasons that the damping ratio may be higher for case two is you have a higher initial deflection where the beam is able to kind of snuff out some of those vibrations faster. With cases three and four, you have dampening ratio increasing compared to case one, which is to be expected as tape was added to the bottom, increasing the stiffness. For the conclusions, the stronger tape led to higher dampening ratio and equivalent stiffness. Beams using first mode of natural frequencies can be simplified into a spring mass dampener system. Sensitivity of the strain gauge can be found by relating voltage to displacement and finding the slope. And finally, equivalent stiffness can be found by relating force and measured deflection. Here are the references, and thank you very much for listening.